Okay, so getting ready for our next presentation. We are going to continue on the theme of climate change modeling by inviting Thomas Selah from the International Institute for Sustainable Development, Experimental Lakes Area, to come talk to us. Thomas is a policy advisor with the International Institute for Sustainable Development. His research focuses on the impact of innovations in data and technology on environmental science and freshwater management. As part of this work, Thomas has been leading efforts to leverage machine learning and cloud computing for analyzing those great big long-term data sets for the Experimental Lakes Area. Please welcome Thomas. Thank you so much.
Thank you, guys. I want to start off by saying I'm really so glad to be at this event, and it's great to see so many people, passionate people here with an interest in tackling these really pressing issues that often don't get enough attention. So, and very happy to have been invited to speak here today. And to follow Paul, it feels like a tough act to follow someone with a lot more experience than I do have yet in this field. But that kind of leading into that, I am not myself a limnologist or a freshwater ecologist. I work primarily with data and software and those kind of fun things, but I talk to a lot of limnologists, and so I'm hoping that I will do justice to some of the things that they've tried to explain to me over the last several years here. So for my presentation today, I'm going to be talking to you about what we do at the Experimental Lakes Area, our research, what we've learned over the last 50 years of research at the Experimental Lakes Area, talking specifically about climate change trends we're seeing in the long-term data that we've collected, and then I'll talk a little bit about my work with machine learning and forecasting and how we can use some of that to our benefit going forward. Okay, so the Experimental Lakes Area. This is an air photo. It's set in northern Ontario near Kenora. It's a landscape that, like much of the Canadian Shield, is kind of pockmarked with lakes. And we use those kind of small lakes to run whole ecosystem experiments. Next slide. So we have over 50 lakes where we run all of these ecosystem manipulations. Sorry, could you go back a couple? Yeah, that's okay. Yeah, so we do physical manipulations in some cases, sometimes chemical, sometimes also work with biota. What you're looking at in the bottom right there, sorry.
I think it's on a timer.
Oh shoot, is there a timer going? Hopefully there's a way to shut it off.
I don't know how to do it.
Maybe
we can just have a quick
Great. So what you're looking at on the bottom right there is a photo of these mesocosms. They're essentially giant test tubes that we kind of drop into the lake when we're testing sort of a section for an experiment. We've done, so like I said, physical manipulations. You're looking at a dam that was built there on one of our lakes. In one case, one of our most well-known early experiments was a curtain that was drawn across a lake where we fertilized both sections differently, and we found that phosphorus was the leading cause of algal blooms in that lake. Maybe the next one, yeah. So we also have been lately, so the ELA used to be under the Department of Fisheries and Oceans. It's now been taken over by the International Institute for Sustainable Development, and we've put a lot of work into building our outreach and education programs. So we invite students over, schools, local communities to visit and do kind of public tours and see the science that we do firsthand. And here's also a note about how I think it's been an important learning trajectory for us to meet with and work with and learn from Indigenous communities in our area. So on the right you have pictures of, this is a water ceremony that was done this year in April after the first melt of the lakes. And at the bottom right there is a picture of us doing some outreach with local communities on their water monitoring programs And some of the things we're learning from elders and working with elders and youth in these communities is the importance of working across generations is really something that's emphasized across the board. And also, thinking, when we're talking about climate change specifically, obviously we're thinking not just about ourselves, the impacts we're already seeing, but we're planning many generations into the future. So these are a couple of things that we've really been learning and emphasizing in our work lately. And one way that we as scientists are trying to do this, and thinking about those 7 generations into the future is our long-term research. So at ELA, of those over 50 lakes, we have 5 long-term ecological research lakes where we've been collecting data continuously for, in some cases, over 50 years on meteorology, hydrology, water quality, and the sort of full food web from algae and phytoplankton up to fish. Okay, now I want to quickly acknowledge that, like I said, I'm not the limnologist, so the work I'm about to talk to you about in terms of our long-term climate research is mostly, has been led by Michael Patterson and Scott Higgins, who are our lead researchers at ELA, and scientists before them, as well as a whole large team of people that's engaged in data collection. So, a quick survey of the kind of 5 main findings that we're finding at ELA from climate change. So, as you all know, our air is getting warmer. That won't come as a surprise. Our lakes are also getting less icy as a result. So we've got a shorter ice-covered season. Our lakes are actually getting darker as well, and somewhat surprisingly, they're actually getting cooler. So I'll explain where that's coming from. The changes in the lakes actually mean that a lot of the fish are squeezed into smaller habitats, even though the volume of the lake isn't changing necessarily, the habitable space is. And therefore our fish are getting smaller and are suffering as a result of that. So this plot is just to give you, I guess, an idea of some of the changes that I'll be talking about are seen across those long-term lakes that I mentioned. So we have here 4 of the long-term ecological research lakes plotted, and the x-axis is really the Pearson's coefficient, so really how confident are we in the changes that we're seeing happening across all of these lakes. And so what we see is the change in whole lake temperature, which actually is, again, getting cooler. That's consistent across our lakes. Transparency of the lake, calcium, dissolved organic carbon, these are changes, even the algal blooms and phytoplankton population, these are changes we're seeing across the board. Some of the other ones are also changing, but the changes are more ambiguous. Okay, so the first one, I won't dwell on it too much because Paul did a great job of explaining this in the previous presentation, but our lakes are definitely getting warmer. We're seeing an increase of 0.5 degree centigrade per decade, or Celsius per decade, which is over the global average. Next slide. In the summer months, we're seeing some of this increase, which is also tracking the global average increase since we've been collecting data, so from the late 1960s to today. Next. And it turns out that the fall and winter temperatures are increasing even more. So it's not super visible on those plots, unfortunately, but what the data is showing is that we have 3 times faster increase in temperature in the winter than we do over the summer. And so as a result, the lakes are ice-free for a longer part of the year. So what we're seeing as a general trend is about 4 days less of ice per decade. Over the last 46 years, that's about 20 days of less ice over the season. And in the long term, we've done a little bit of work looking at climate models, and it looks like that trend will be looking at over a month of more ice-free time by 2070. Next slide. Okay, so what controls the surface temperature of a lake, right? We have obviously the radiations coming in from the sun, and then we have heat loss from contact through the air and from radiation up out of the lake. what we're seeing, what you can see on that plot on the right is that the surface temperature of the lake more or less tracks with air temperature. So as the air gets warmer, the surface temperature of the lake follows pretty closely. But perhaps in our case at ELA, the bigger factor in what's changing the living conditions for life in those lakes is that it's actually getting wetter. So we're seeing increased precipitation on average over the years. This is a trend that, interestingly, at least around Kenora, there seems to be a sort of 30-year cycling of dry and wet periods. But what seems clear is even despite that, there's a trend upwards in the amount of precipitation we're getting. Next, yeah. So what does this mean? So if there's more rain coming down on the landscape, that means that it's draining more soil and more leaf litter and things into the lake. So we get more of this dissolved organic carbon. That's what gives lakes their sort of brown color. And if there's more of that dissolved organic carbon, what the infographic on the right is showing is that light actually doesn't penetrate as deeply when the lake is darker, which means there's the cold section of the lake, which is called the hypolimnion. That part gets bigger, and this thermocline. So if you were to dive, and usually this is too deep for you to notice when you're swimming, but if you were to dive 15 meters down into the lake, you'd reach this point where the lake temperature drops very suddenly from, let's say, 15 degrees Celsius down to about 4 degrees, right? Which is very, very cold. So, but this has a lot of significance for the fish and where they can live, right? So we have this what we see is as the dissolved organic carbon goes up, these lakes are getting colder, and the photic zone, which is where plants are able to grow, where we're able to get algae and more life, that zone is also getting smaller. So to recap, what we're seeing is an increase in precipitation. Next slide. That leads to dissolved organic carbon getting into the lakes, which means darker lakes. And that means a shallower thermocline, which again means that the lake on average is getting cooler. Next. Another effect that all of this leads to is, again, coming back to that dissolved organic carbon coming into the lake. As it sits in the lake, it is feeding bacteria and other micro life in the lake that is decomposing that carbon, and that actually burns oxygen. So the deepest part of the lake, which doesn't mix, it's a standard 4-degree temperature, there's really very little cycling going on in there. That part of the lake, over time, the bacteria use up all the oxygen in the bottom portion of the lake. Could you go to the next slide? So what does this mean? If we look at sort of a plot over the course of a year, that we can think of that white section as the sort of habitable zone for cold water fish. We're thinking like lake trout, for example. And what we have is this sort of Goldilocks problem where the upper portion of the lake in the summer, after the ice has thawed, is too warm for their comfort. And the bottom portion of the lake is livable. There might be less food down there. It's also, as I was saying, the oxygen slowly gets depleted. And so what we see in the later portion of the season is the fish are squeezed into a relatively small, sort of 2-3 meter portion of the lake. And so what does all this do? So as, again, those ice-free seasons are getting longer, which means, again, more oxygen depletion, the water gets warmer. So what happens is these fish, since they have less livable space, we're actually seeing over time, we've been monitoring fish for, again, close to 50 years. This goes back, I think, to 1986. We see that the average lake trout size was about 450 to 500 millimeters of fork length, and that's decreased significantly over the last 20 years. So the population hasn't gotten smaller necessarily, but the average size of the fish is smaller and they're generally less healthy. Yeah, so this is again sort of confirming that and what we're sort of seeing, and again, that kind of shift in fitness. So the reduced, not just reduced length, but also their skinnier and reduced mass of the fish. Okay, so that's a lot of bad news. But the question is, what do we kind of, obviously we're here to start thinking about what we can actually do about some of these things. So it's obviously good to know what the problems are, but how do we respond to them? Next slide. Okay, so at ELA, in terms of how we actually do our science, we've been noticing a few things that we're trying to take steps to remediate. So we are concerned about invasive species. We've so far been able to sort of keep them at bay, but we've increased our broad-scale monitoring. So our fish monitoring crew that goes out and they cycle through these 50 lakes and collect fish and count them and measure their size and all of these kinds of things. They've also been now keeping an eye out for small invertebrates, and other kind of small life in the lake that could be of concern. So climate change also presents a challenge with interpreting historical data, right? And doing new lake experiments. So it becomes harder and harder to tell if you have longer term data on this lake and you want to do an experiment on it. What is a change signal from climate change versus from some other work that you're doing? So we've been making improvements to how we handle our data to try and accommodate that. There's also technological changes which bring a lot of positives. So there's a lot of new technologies that are coming out, and we have water rangers here who are provide test kits, and a lot of the technology that they are using is relatively new. So it means we can do more sampling. Volunteers can do more sampling. In our case, we can also set up networked systems that are deployed to the lake over the whole summer or sometimes year round and can collect data for us and send it to our computers directly. And the changes in ice cover. So that for our scientists, that means sometimes an earlier field season, sometimes the field season lasts longer, and so we're trying to plan around that. And this is where some of our later work around machine learning comes in. So we're getting into forecasting the ice cover. Okay, so ice off. Again, I talked about how the ice-free season is longer. That's especially driven by the fall increase in temperature, so ice is forming later in the season. Ice formation in the spring is becoming less predictable, but it's also, we're not seeing as clear of a trend of earlier melt as we might be seeing in other parts of the country. Next slide. So we had done previous research to figure out where all of these ice changes are coming from, but the next question we wanted to get into is, can we actually start to predict not just on say a 20-year running average, but this year, when is the ice going to thaw? And this could have applications obviously for our research, but these are models that folks are also working on across Canada to figure out, for example, when ice roads are no longer safe to use, or when you might be able to, how fish populations might be impacted, because though those freezing and thawing, I talked about dissolved oxygen, those freezing and thawing is the one period in the year when the full lake mixes, and that ice can melt and that cold water sinks to the bottom and warm water is dragged up, and so that oxygen gets into the lake and the lake gets refreshed that way. So, biologically, it's also an important period of the year we're trying to understand. So, as I mentioned, we have these network systems. What you have on the left there is a raft with a solar panel and a sensor that we've deployed there that sends our data up to a satellite network. We have been working on our database to make sure that everything is connected and makes sense and scientists can reach it quickly and easily. So, and that sort of forms the groundwork for the forecasting piece. So could you go to the next slide? So before we get into that, I guess one note I'll make is that obviously all of this data comes from a lot of hard work in the field. Our data collection team and our meteorology and limnology team are there year-round collecting data for us on ice cover, the depth of ice cores, all summer collecting temperature and all sorts of dissolved oxygen and all sorts of other data from our lakes. So it's a lot of hard work, and I just want to also echo that the work that gets done by volunteers and by people around the country collecting this data is vitally important for the research that we do. Okay, so once that data is there, there's a lot of work that goes into making sense of it. So in terms of, ahead of doing any of this forecasting or modeling work that we do, a lot of work has gone into digitizing our data, so a lot of handwritten notes that get put into computers. We've put that into a relational database. We've built quality control processes for our scientists to make sure that the data makes sense and is aligned with, that there aren't any quality concerns with the data. Then there's other improvements that have been made along the way as well. We're also working on, again, some automation network processes to make all of this run a little bit smoother. So there's a lot of technology emerging that will hopefully make all of this stuff in the long run easier and more convenient to use. So again, in terms of how we did our analysis, our y variable, if you think of that x variable that we're putting in, the y is what we're trying to predict. So our dependent variable was the days until ice off. So the way we thought of it was, if you take any day, say you're in February and 5th, and we don't know when the ice off date, we're trying to get a model to tell us the ice off is going to be in 30 days or 45 days or whatever. And in terms of how we build a forecasting model, what we have to work with is a long time series of our data over many years. And what we're trying to do to train the model on is to say, if I take again some date, February 5th, let's say, the model, in order to come up with a forecast, it needs to look backward at the data that preceded that. So we're looking at what was the average temperature over the last week, what was the snow cover over the last week, same thing last month, last 24 hours, right? So there's all of this stuff that we're kind of building into the model to build a correlation there. Oh, that didn't display properly. That's okay. So, okay, but what's he doing there? No. So I like to think of these machine learning models a little bit like your dog, right? You're trying to train your dog, and you give it treats, and you're trying to get it to tell you, in our case, how many days until ice off. Your dog's not going to be able to figure that out. But the idea being there's a little bit of a balancing act when you're training a dog in terms of how often do you reward it and what do you reward it for, right? And how much information you give it. You don't want to overwhelm it with too many instructions that it's not going to understand off the bat. So you have to start small and build up. And if you reward your dog for too many things, it's going to end up with a bunch of behaviors that you're not intending, right? And so, could you maybe try clicking? Yeah, there we go. Okay. So it's the same idea with a machine learning model. So if you have to kind of calibrate the reward properly, otherwise you'll get a problem that's called overfitting, where the model is fitting very closely to the data that you gave it for, say, the last 10 years, but then you give it a new year's data, and it's way off because it's assuming things that aren't necessarily true of the new data you're giving it. So there's a lot of work. I don't need to get into the details of that necessarily, but we do, when you get into the machine learning portion of it, we had a lot of learning to do on our side of how to sort of fine-tune that model to get the reward right and to give it the right amount of information, again, not overwhelm it with information. As a final step, what we did was we built a user interface online for our research team to be able to access the model and get a prediction on what the model was saying about when the ice would melt. So if you look at, 2024 was our first year testing out this model. The prediction on March 7th was that the ice would be off by April 30th. Prediction on April 10th was that ice would be off by April 25th. Next. Turns out it was off by a little bit. So May 6th, it was off by about 1 to 2 weeks. So after all that work, there's still these things are imperfect. At the same time, we did have, and climate change presents a challenge here because we had, again, an unusual year, which increasingly unusual is usual. So what happened is we actually, our field team was following this model closely, and they were out on the lake every day to see is it thawing, and we saw all the signs of ice melt. So we started to see what's called bowing in the lake, and we were seeing, moating, and water forming kind of along the edges of the lake and things. But we got a cold snap, and everything froze again for about a week. So even with the best models, you can't get it 100%. So what I'm trying to, I guess after all of this, I guess the point to walk away with here, when it comes to climate change especially, I think our adaptation efforts and our mitigation efforts and all these things, it's, in my read of it, slow and steady wins the race. So we have benefited from the gifts of previous generations. None of the original researchers at the Experimental Lakes Area are there, working there today to, so many of them are aware of these findings, but some of them have passed on, right? And so, but they've left us with this great legacy of research and information and an institution that has become a bit of a Canadian institution. And even when we mention previous generations, it's everyone who's kind of cared for the land before us, right? And who's made sure that the land is in a place where it's healthy enough for us to be living on it and to be learning from it. And even with new technology, right? I talked a lot about these machine learning efforts. It took us a lot of time to figure out how to get this thing working, right? And what we spend months on now, sometime in the future, people will get a hang of it, and maybe they'll become easier to use and all those kinds of things. But I think it takes a certain amount of patience and dedication to figure out what these new technologies can do for us and how we want to use them to the best of to their best potential. So, I think the biggest thing, and we learned this from coming out to events like this, from presenting on our research, from our education and outreach efforts, is that our lakes really are a part of our identity as Canadians. And so I think we all love our lakes, and so I think that is hopefully a little bit of encouragement to keep this going. Thank you. Any questions?
Mel's just going to turn on the question mics and start passing them out. So if anybody does have any questions, please put up your hands and we'll get you a microphone in just a moment.
Thank you, Thomas. You certainly presented us with a lot of information. Unfortunately, a lot of it we really can't do much about, but I have a question about your experimental lakes area.
Yeah.
Do you have any zebra mussels in those lakes?
Currently, no. We've managed to keep them out. There's issues in a lot of surrounding areas, but we've got fairly careful practices around that so far. But I mean, yeah.
So I'm from the Charleston Lake area.
Yeah.
We have zebra mussels. We've had them probably since about 2000.
Yeah.
Our lake is way clearer than it ever was before. We have Secchi disc readings that are unbelievable. Our lakes are a lot clearer. And we're facing a lot of other issues too with some blue-green algal issues we're seeing now. But anyways, any of the things that you discover do they ever get put into, passed on to the government and then put into a legislated things for our lakes, like health, like setbacks from the water for, growth, let the stuff grow for 15 meters, or put your lawnmowers away, and things like that?
Yeah, absolutely. So I think, these policy change takes a lot of time. And I think the best examples are from the early periods of the Experimental Lakes Area, because it took, many years for those policy changes to take effect. But I mentioned that experiment near the top of the presentation where we pulled a curtain across a lake and we found that phosphorus was the main contributor to algal blooms. That actually drove a lot of policy changes both in the US and in Canada around regulating phosphorus in cleaning products, so removing that to help with that. We're also looking at other sources of phosphorus and how they can be reduced. So we've also done research around acid rain. I think part of the concept behind the International Institute of Sustainable Development partnering with the Experimental Lakes Area was to try and build that connection between the scientific research and the kind of policy work that gets done at IISD. So we do take that very seriously and we work towards that, yeah.
Thank you.
I'd just like to ask a
Sure.
question regarding the research you're doing in terms of open access. Do you have an open access policy with the Experimental Lakes program?
By open access, do you mean the research or the data, or?
Published literature,
Pub-
and I don't know how much you do it with ongoing
Yeah.
databases, but I mean, published research.
Yes, so as a general, so I'd say it really depends, because a lot of our work actually gets done through partnerships with academic institutions. So we have, all sorts of researchers coming from universities across Ontario and Manitoba and other parts of the country to come in and do their work, and it's sort of we try to encourage open access, because we think of this the Experimental Lakes Area as sort of we benefit from working with the government of Canada, with the public, and so we want that to be returned. So we, on our side, work towards it, but it ultimately is on a project-by-project basis. On the data piece, we've been working for a while now on publishing lots of our data sets to public repositories. So right now we have some of our data is on DataStream, which is a platform for collecting water quality data across Canada. We have some of our hydrological data, so how much water is running through the lakes, through the weirs, etc. Some of our plankton population data is up on DataStream. So we're on environmental data initiatives. So these are things that we're also working towards. Yeah.
Okay, thanks very much.
Thank you very much for a really interesting and important presentation. Okay, good. Thank you very much for an informative and important presentation. Just a couple comments. First of all, thank goodness the Government of Canada was clever enough to set up the Experimental Lakes 50-odd years ago, because good heavens, you're trying to, what, you would experiment in a lake? Are you kidding? So glad it happened. And when the federal government finished funding for that, because apparently it was no longer necessary, thank goodness your organization stepped in. And the reason for that is these data sets that are available, the interpretations that you've made, are local to us, although you're on the other end of the province sort of thing, very similar geology and ecosystems. So even though it was done remotely from this part of the world, these results are very meaningful to demonstrate what is going on, what is changing, what's happening. And this gets back to the comment about adaptation versus mitigation. Well, we need to understand what's happening before we can start to adapt. And once we know why it's happening, then we can start to mitigate. Getting rid of phosphorus is a beautiful example of that. So thank goodness your work is continuing. And the fact that it's, it's all going out through the published scientific literature to make it even more accessible in open data sources, so citizens can start to access your data. Maybe, some clever kids will come up with some, new ideas that scientists haven't. So keep up the good work. Thank you.
Thank you.
Thomas, thank you for your presentation. As a much younger man, I actually spent a day at the Experimental Lakes when I was working up in Rideau, and I found it extremely interesting. At that time, there was quite a controversy around your funding, your sustainable funding, and your federal government, and they were looking at pulling out, and unfortunately they did not. But my question to you is, how is your funding handled now, and is it sustainable? Is it provincial, federal, private, foundation? And how are you looking at that going forward?
Thanks, great question. Yeah, so that's changed a lot over these. I guess I'll do a quick recap for those who aren't aware of the history of the Experimental Lakes Area, so it seems relevant based on this question. So the Experimental Lakes Area, which was founded in the early 1960s under the Department of Fisheries and Oceans, and it stayed there for about 40 some odd years, and I believe it was 2011 was being shut down by the federal government. It was then taken up by the International Institute for Sustainable Development and has been operated by IISD since then. In terms of where our funding comes from, so that's changed obviously since moving away from Department of Fisheries. We do still get some funding from the Department of Fisheries as well as from the province of Ontario. We also work with academic institutions as well in terms of the research grants and those kinds of things. And there are also partnerships with the private sector. So, for example, a lot of my work actually gets funded by the RBC Tech for Nature Fund. So we have a lot of different funders kind of across the spectrum, which I think gives us a little bit of stability in terms of being able to sustain all of this going forward. I also want to kind of note that we've had pushback over the years. The previous question or comment mentioned this, that ELA is a bit of a unicorn. It was founded in the 60s around doing experiments on whole lakes, and that has become an increasingly controversial proposition, right? So it would be very hard to create something like ELA today. At the same time, I think this is something that the research teams all take very seriously, and there's a kind of an understanding that when we do a whole lake experiment, which are occasional, we understand that the lake is really taking one for the team, and so there's a lot of effort that goes into monitoring and planning for remediation of that lake, and we make sure that the research is well worth it, and that we're going to have hopefully a big impact on the science and on improving the conditions at other lakes.
Any other questions?
Just a quick question. Do you use the Lake Partners data?
I'm not aware of the Lake Partners data, actually.
Oh, because I know they have a lot of data from years and years and years, and it would be great if you were using it, because then we could get more people sampling in more lakes, like our lake associations could. If we could connect it with you guys, it would be wonderful.
I think that's an excellent point. We've been thinking a lot through our, I mentioned our education and outreach programs. We've been thinking a lot about how to, connect our research with the data that's being collected by volunteers across the country through Lake Partners and other programs as well. We know of the Water Rangers are here. Lake Winnipeg Foundation is another big partner of ours. So
You can also talk to Leslie Lavender about Lake Partner Program.
Excellent.
Sorry, I'm not a public speaker. Do you think machine learning that we're entering a new kind of renaissance where a lot of people are using machine learning and the training's happening really quickly, or are we still really very much at the birth of this kind of information and the work that you're doing?
It's a good question. I would say it's somewhere in between. I mean, machine learning has been going on for a while. The newer technologies, we all are familiar with ChatGPT and all these kinds of things. There's, a lot of progress that's been made over the last, 10 years or so that is making its way around different sectors. I think there's a lot of enthusiasm right now around machine learning, and we're going to have I don't want to say, well, we're going to have some disappointments in some areas where, it can't do everything that we want it to do necessarily, and a big thing with machine learning is that, they say often in data analysis, garbage in, garbage out. So if we don't have enough data, good quality data from around the country, then the machine learning can't really do very much. So I think the big part that I hope we see more investment in from the government, from organizations across the country, from folks, from volunteers and communities, is to continue to invest in those data sets that we really need.
Any other questions?
You've got the mic, you go ahead.
If it works, I'm not sure.
There you go. You got it.
Yeah, we can hear you.
Just a matter of interest, what's your labor force currently in terms of how many are involved in the LA?
So it's very seasonal work. We do a lot of partnerships with graduate programs. So in the summer, and if we're counting the entire staff at ELA, we're often over 50 people, 50, 60 people. Sometimes, a lot of researchers don't actually stay at ELA as well, so they might have field teams at ELA and they might be, working remotely, they're teaching at a university, et cetera, and they make occasional visits out. So it's hard for me to give you a complete number, but that is about the amount that we're talking.
Is that comparable to years past?
It's grown. So there are certainly more people there, and I know this, I wasn't around at that time, but I know that 10, 15 years ago, it was a smaller cohort of people in the summers. We're making investments on improving the facilities there, and also along sustainability lines. So we're building a solar station, and we're going to have most of our energy be renewable in the coming years.
Thanks for your talk. Just wondering about data collected by satellite. Is there any role for satellite?
Yeah, great question. I think the short answer is yes, definitely. Like remote sensing from satellites, also LiDAR, so low-flying planes and things, has provided a lot of useful information for the research that we do. So at ELA, I think it's less of a necessity because we have people on the ground collecting very high fidelity data, and the remote sensing data is of great quality when we're talking about large scale landscapes of understanding what's going on at like a whole ecosystem scale. So in terms of our work and what we do, we have some applications for it. For example, digital elevation maps we use to figure out where the watershed delineations are, so where the water is coming from into the lakes. Those are the sorts of applications. And beyond the Experimental Lakes Area, we at IISD do work working with watershed districts on using the satellite data to do things like figure out, for example, crops and farming and the impacts on water quality. So the Government of Canada has an annual crop inventory that they publish from satellite data every year, And that is an example of data set that's really useful to us for some of our work, like promoting nature-based solutions for water management and improved water quality. So, yeah.
Anybody else? Okay, great. Well, thank you so much for coming. It seems we've run out of questions for now, but don't go far. We do have a little treat for you for making the trek all the way from Toronto. Thank you so much. And always happy to hear more about the Experimental Lakes Area. Thank you so much, Thomas.